Today, we will discuss numerical problems on forced vibration and transmissibility in vibration engineering. The first question is a vertical single stage air compressor having a mass of 500 kg is mounted on springs having stiffness of 1.96 into 10 to the power 5 Newton per meter and zeta is given, that is 0.20. The rotating parts are completely balanced and the equivalent reciprocating parts weigh 20 kg. The stroke is 0.2 meter. Determine the dynamic amplitude of vertical motion and the phase difference between the motion and excitation force if the compressor is operated at 200 rpm. First of all, we see that m is equal to 100 kg is given, k is equal to 1.96, that is the stiffness of spring. K is equal to 1.96 into 10 to the power 5 Newton per meter. The value E is equal to 0.20 and m naught 20 kg and the eccentricity is equal to 0.1 meter is given. We have to find the amplitude and the phase difference phi and force. For this we have to find the value of omega n, that is equal to root k by m. The value of k is given, that is 1.96 into 10 to the power 5 upon 500, that is equal to 19.79 radian per second. And then we find the value of omega, because we have to find the ratio of omega and omega n. For omega, that is equal to 2 pi n divided by 60 is equal to the value of n is equal to 200 rpm is given, that the value of omega will be 20.93 radian per second, and the ratio of omega by omega n is equal to 1.057, and the square of this is equal to 1.11. Now for rotating unbalance, we have the formula that a by m naught e by m is equal to r square upon in root 1 minus r square the whole square plus 2 zeta r whole square. Here the r is equal to omega by omega n. By putting the value of m naught e and m, then we get the amplitude value, that is equal to 0.01 meter. And the phase difference that is equal to tan inverse 2 zeta r upon 1 minus r square. Here the value of zeta is equal to 0.20 and the r 1.057. By solving this we get the value of phi is equal to 105.9 degree. The another question is a 1000 kg machine is mounted on four identical springs of total spring constant K and negligible damping. The machine is subjected to a harmonic external force of amplitude F is equal to 490 Newton and the frequency 180 RPM. We have to determine that the amplitude of motion of machine and maximum force transmitted to the foundation because of unbalanced force when K is equal to 1.96 into 10 to the power 6 Newton per meter. For this, first of all, we have to find natural frequency omega n, that is equal to in root K by M. By putting the value of K and M, we get the value of omega n, that is 44.27 radian per second, where omega is equal to 2 pi n by 60. The value of n is equal to 180 rpm and is equal to 18.84 radian per second, and the ratio of omega and omega n is equal to r is equal to 0.425, and the square value of this, then r square is equal to 0.181. Now you have to find the force, that is, force is given in the question, that is 490 Newton, and we know that the formula of force, that is Fyk is equal to 490, that is equal to deflection. Fyk is equal to the deflection by the spring formula F is equal to Kx. Then deflection is equal to 2.5 into 10 to the power minus 4 meter. We know the relation amplitude upon F by K is equal to 1 minus in root 1 minus r square, the whole square. By putting this value of A, F, K and R, then we get the value of amplitude. Here the amplitude we have to find, that is equal to 3.05 into 10 to the power minus 4 meter. Now the force transmitted means the force which is transmitted to the foundation, that is Ft by F is equal to 1 by root 1 minus r square whole square, and we get the value of Ft is equal to 598.3 Newton. And in case when the rotor is mounted midway on the shaft, the static deflection is given by in the mechanics of solids. For we can find the formula of deflection, that is equal to WL cube 48 EI. Here the value of W, that is 39.24, and putting this value we get the deflection, that is 1.33 into 10 to the power minus 4 meter, and the omega A is equal to the in root g by del, that is equal to 271.5 radian per second. Thank you.